Harmonics can indeed be intermittent, varying in both magnitude and frequency based on load conditions and equipment operation within the power system. Now, can harmonics cause transients? Yes, harmonics can contribute to transients through several mechanisms. Firstly, resonance. Harmonics can resonate with power system components such as transformers and capacitors, leading to the creation of high-frequency currents, and these high-frequency currents can in turn cause voltage spikes. Secondly, capacitive coupling. Harmonic currents as they flow through capacitors can induce voltage impulses in other connected circuits. Thirdly, inductive coupling. Harmonic currents flowing through inductances, such as transformers and motors, can generate transient voltages, especially when the current changes rapidly. The transient voltages observed of up to 217 volts on a 480 volt system signify a significant problem that demands immediate attention. While harmonics might contribute, they are unlikely to be the only cause. To address this issue, consider several steps. 1. Conduct a thorough investigation to pinpoint the sources of harmonics and transients within your system. This involves analyzing load conditions, equipment operation, and the overall power system configuration. 2. Implement harmonic mitigation measures. If harmonics are indeed a major contributor, consider installing harmonic filters such as passive filters or active filters to reduce their levels. 3. Install transient voltage surge suppressors. Transient voltage surge suppressors can protect sensitive equipment from transient voltages. Consider installing them at critical locations within your system. Depending on the investigation's findings, additional measures may be necessary to mitigate transients. These could include grounding improvements, the use of isolation transformers, or surge arresters. It is important to note that the specific measures needed to resolve your specific transient problem will depend on the underlying causes identified through a detailed investigation. Let's delve into the specifics of harmonics, transients, and potential solutions for your 480 volt system. Harmonics are essentially distortions of the ideal sinusoidal waveform of alternating current or voltage. These distortions occur at frequencies that are integer multiples of the fundamental frequency, which is typically 60 Hz in the United States. For example, the second harmonic is twice the fundamental frequency, or 120 Hz. The third harmonic is 180 Hz, and so on. These harmonics are generated by nonlinear loads, which are devices that draw current in a non-sinusoidal manner. Common sources of harmonics include electronic devices like computers, variable frequency drives, also known as VFD, and uninterruptible power supplies. When these non-sinusoidal currents flow through the power system's impedance, they create voltage distortion, leading to harmonic voltages. The presence of harmonics can cause a multitude of problems. One problem that harmonics can cause is equipment overheating. Harmonic currents increase the root mean square, or RMS, current flowing through conductors and equipment, leading to increased resistive losses. This can cause transformers, motors, and cables to overheat, reducing their lifespan and potentially leading to failure. Another problem that harmonics can cause is equipment malfunction. Harmonics can interfere with the operation of sensitive electronic equipment, causing malfunctions, data errors, and reduced performance. Another problem is capacitor failure. Capacitors are often used in power systems for power factor correction. However, harmonic voltages and currents can cause capacitors to overheat and fail prematurely. Another problem is nuisance tripping. Harmonics can cause circuit breakers and fuses to trip unnecessarily, disrupting operations and leading to downtime. And yet another problem that harmonics can cause is increased energy losses. Harmonic currents increase the overall energy losses in the power system, leading to higher electricity bills. Transients, on the other hand, are short-duration, high-amplitude disturbances in the voltage or current waveform. They can be caused by a variety of factors, including lightning strikes, switching operations, and equipment failures. Transients can be classified into two main categories: firstly, impulsive transients, and secondly, oscillatory transients. Impulsive transients are characterized by a sudden, unidirectional change in voltage or current. They typically have very short rise times and decay times. Lightning strikes and electrostatic discharge are common causes of impulsive transients. Oscillatory transients, on the other hand, are characterized by a damped sinusoidal waveform. They are often caused by switching operations such as energizing a capacitor bank or de-energizing an inductor. The effects of transients can be severe. Transients can damage or destroy sensitive electronic equipment, leading to costly repairs and downtime. They can also cause data corruption, system crashes, and safety hazards. In your specific case, the transient voltages of up to 217 volts on a 480 volt system are a significant concern. These transients could be damaging your equipment and disrupting your operations. A thorough investigation is necessary to identify the sources of these transients and to implement appropriate mitigation measures. As mentioned earlier, harmonics can contribute to transients through resonance and coupling. Resonance occurs when the frequency of a harmonic current coincides with the natural resonant frequency of the power system. This can lead to a significant amplification of the harmonic current and voltage, resulting in transient overvoltages. Capacitive coupling occurs when harmonic currents flowing through capacitors induce voltage impulses in other connected circuits. This can happen when capacitors are located near sensitive electronic equipment. Inductive coupling occurs when harmonic currents flowing through inductances generate transient voltages when the current changes rapidly. This can happen in transformers and motors. To mitigate the effects of harmonics and transients, you should consider a combination of measures. The first is harmonic filtering. Harmonic filters are designed to reduce the levels of harmonic currents and voltages in the power system. There are two main types of harmonic filters, namely passive filters and active filters. Passive filters consist of tuned circuits that are designed to block specific harmonic frequencies. They are relatively inexpensive and easy to install, but they can be bulky and can only mitigate a limited number of harmonic frequencies. Active filters, on the other hand, use electronic components to actively cancel out harmonic currents. They are more expensive and complex than passive filters, but they can mitigate a wider range of harmonic frequencies and can adapt to changing load conditions. The second measure is transient voltage surge suppressors. Transient voltage surge suppressors are designed to protect sensitive electronic equipment from transient voltages. They work by diverting the transient current away from the equipment and safely to ground. GVSS devices are typically installed at the service entrance of a building and at critical locations throughout the power system. The third measure is grounding improvements. Proper grounding is essential for mitigating transients. A well-designed grounding system provides a low-impedance path for transient currents to flow to ground, reducing the voltage stress on equipment. The fourth measure is isolation transformers. Isolation transformers can be used to isolate sensitive electronic equipment from the power system. They provide a barrier to harmonic currents and transient voltages, protecting the equipment from damage. The fifth measure is surge arresters. Surge arresters are designed to protect equipment from lightning strikes and other high-voltage surges. They are typically installed at the service entrance of a building and at critical locations throughout the power system. In addition to these measures, you should also consider the following. Implement a regular power quality monitoring program to track harmonic levels and transient activity. This will help you to identify potential problems early on and to take corrective action. Conduct a thorough investigation of any equipment failures to determine if harmonics or transients were a contributing factor. Train your employees on the effects of harmonics and transients and on the proper operation of equipment. By taking these steps, you can significantly reduce the risk of damage to your equipment and disruption to your operations. Now let's dive deeper into the specifics of harmonic filters. As mentioned earlier, there are two main types of harmonic filters, namely passive filters and active filters. Passive filters are relatively simple devices that consist of inductors, capacitors, and resistors. They are tuned to specific harmonic frequencies and provide a low impedance path for these frequencies to flow to ground. This reduces the amount of harmonic current flowing through the rest of the power system. Passive filters are typically used to mitigate low-order harmonics such as the third, fifth, and seventh harmonics. They are relatively inexpensive and easy to install, but they can be bulky and can only mitigate a limited number of harmonic frequencies. Active filters, on the other hand, are more complex devices that use electronic components to actively cancel out harmonic currents. They work by injecting a current that is equal in magnitude and opposite in phase to the harmonic current. This effectively cancels out the harmonic current, reducing the amount of distortion in the voltage waveform. Active filters can mitigate a wider range of harmonic frequencies than passive filters and can adapt to changing load conditions. However, they are more expensive and complex than passive filters. When selecting a harmonic filter, you should consider the following factors. Firstly, the harmonic frequencies that need to be mitigated. Secondly, the amount of harmonic current that needs to be reduced. Thirdly, the load conditions of the power system. Fourthly, the cost of the filter. Fifthly, the space available for the filter. Transient voltage surge suppressors, or TVSS, are another important tool for mitigating the effects of transients. TVSS devices are designed to protect sensitive electronic equipment from transient voltages by diverting the transient current away from the equipment and safely to ground. There are several different types of TVSS devices available. The most common type is the metal oxide varistor, or MOV. MOV are voltage-dependent resistors that have a high resistance at normal operating voltages and a low resistance at high voltages. When a transient voltage occurs, the MOV resistance drops, diverting the transient current to ground. TVSS devices are typically installed at the service entrance of a building and at critical locations throughout the power system. They should be sized appropriately for the voltage and current levels of the system. When selecting a TVSS device, you should consider the following factors. Firstly, the voltage rating of the device. Secondly, the surge current capacity of the device. Thirdly, the response time of the device. Fourthly, the clamping voltage of the device. Fifthly, the location where the device will be installed. Grounding is another critical aspect of power quality. A well-designed grounding system provides a low impedance path for transient currents to flow to ground, reducing the voltage stress on equipment. The grounding system should be designed in accordance with the National Electrical Code, specifically Article 250. The NEC specifies the requirements for grounding and bonding of electrical systems. The grounding system should include a grounding electrode system, a grounding conductor, and a bonding conductor. The grounding electrode system should be connected to a grounding electrode such as a ground rod, a ground plate, or a metal underground water pipe. The grounding conductor connects the grounding electrode system to the neutral point of the electrical system. The bonding conductor connects all non-current carrying metal parts of the electrical system to the grounding system. This includes equipment enclosures, conduit, and cable trays. Proper bonding is essential for preventing voltage differences between different metal parts of the electrical system. These voltage differences can create a shock hazard and can also damage equipment. In addition to these measures, you should also consider using isolation transformers. Isolation transformers provide a barrier to harmonic currents and transient voltages, protecting the equipment from damage. They work by magnetically coupling the primary and secondary windings, but they do not have a direct electrical connection between the windings. This isolates the equipment on the secondary side of the transformer from the power system on the primary side of the transformer. Surge arresters are another important tool for protecting equipment from lightning strikes and other high-voltage surges. Surge arresters are typically installed at the service entrance of a building and at critical locations throughout the power system. They work by diverting the surge current to ground, protecting the equipment from damage. Surge arresters are typically metal oxide varistors that are designed to withstand high surge currents. They are connected between the phase conductor and ground. When a surge occurs, the surge arrestor's resistance drops, diverting the surge current to ground. It is important to note that the specific measures required to resolve your specific transient problem will depend on the underlying causes identified through a thorough investigation. You should consult with a qualified power quality engineer to conduct a thorough investigation of your power system and to recommend appropriate mitigation measures. A power quality engineer can use specialized equipment to measure harmonic levels, transient activity, and other power quality parameters. They can then analyze the data and recommend solutions to improve your power quality. In addition to the technical aspects of power quality, it is also important to consider the economic aspects. Poor power quality can lead to increased energy losses, equipment failures, and downtime. These factors can significantly increase your operating costs. By investing in power quality improvement measures, you can reduce your operating costs and improve the reliability of your electrical system. The cost of power quality improvement measures will vary depending on the specific measures that are implemented. However, in many cases, the benefits of improved power quality will outweigh the costs. For example, installing harmonic filters can reduce energy losses and prevent equipment failures, saving you money on your electricity bill and repair costs. Installing TVSS devices can protect sensitive electronic equipment from damage, preventing costly repairs and downtime. In conclusion, harmonics and transients are significant power quality problems that can cause a variety of issues. These issues can range from equipment overheating and malfunction to data corruption and safety hazards. In your specific case, the transient voltages of up to 217 volts on a 480 volt system are a serious concern that requires immediate attention. To mitigate the effects of harmonics and transients, you should consider a combination of measures. These measures should include harmonic filtering, transient voltage surge suppressors, grounding improvements, isolation transformers, and surge arresters. You should also implement a regular power quality monitoring program and train your employees in the effects of harmonics and transients. By taking these steps, you can significantly reduce the risk of damage to your equipment and disruption to your operations. Remember to consult with a qualified power quality engineer to conduct a thorough investigation of your power system and to recommend appropriate mitigation measures. This engineer can help you assess your specific needs and recommend the most cost-effective solutions for improving your power quality. A well-designed and implemented power quality improvement plan can save you money, improve the reliability of your electrical system, and protect your equipment from damage.